Dear learners, I welcome you to the Senior High School Mathematics, previously called Core Mathematics. So for this course, we are going to look at all the topics that we can get in the Senior High School Mathematics for Year 1. Yes, so we shall be taking them topic by topic or subheadings by subheading, and we treat each of them. All right. So let's look at our first topic. What we are going to look at in the first topic, we shall talk about real number system. Real number system. And in the real number system, our lesson 1 is going to focus on real numbers. Real numbers. So we shall be looking at sets of numbers in real number system. Now let's recall what we learned in the junior high school mathematics under real number system. So I'm going to give you 5 seconds, and I would like each and every one to think and recall some of the set of numbers we learned in the junior high school mathematics under real number system. So I'm giving you 5 seconds. Think about it. All right. All right. Now, what are some of the set of numbers under real number system that we can recall in the junior high school mathematics? Now, we can talk of whole numbers. Whole numbers. We can also talk of natural numbers, integers, rational numbers, irrational numbers. So if you mention these set of numbers, then you are right. So these are some of the set of numbers we read in the junior high school mathematics. So for this topic, our first lesson, or our lesson 1, is going to be on real numbers. But before that, let's list some examples of whole number, or let's also list some examples of natural numbers, and then we also look at examples of integers. Okay, so in the junior high school mathematics, we learned that when we talk of whole numbers, that is, we normally used capital W to denote whole numbers. So let's list some examples. Remember, we said in the junior high mathematics that whole numbers start from what? 0 to the infinity. So I'm starting from 0. I have my 1, 2, 3 to infinity. To infinity. Okay, so the 3 dots suggest that there are other numbers that, apart from the first 4 numbers of whole numbers, we can also talk about, but we can't list all of them because it is to the infinity. All right, so let's also list some examples of natural numbers, which is also called what? Counting numbers. And we also said that in JHS, we also said natural numbers start from 1 to the infinity. So I'm just listing them. Okay, to the infinity. Good. So these are whole numbers. If we have this, then we can probably say that natural numbers are a subset of what? Whole numbers, because we can get all natural numbers in whole numbers, but we can't get all whole numbers in natural numbers, because we have 0 in whole number, but we don't have 0 in natural number. Okay, let's also write examples of integers. Remember, we use Z to represent or denote what? Integers. Yes. So these are also examples. So what did we say integers are? We said that they are infinite positive and negative whole numbers, including what? Zero. So these are integers. So integers are what? Both infinite positive and negative numbers or whole numbers, including what? Zero. So infinite negative numbers. So I can write here as -3, -2, -1. I have my 0, +1. We have 2. We have 3 to infinity. Okay, good. So these are some of the examples of integers. Okay. All right. Now we also talked about rational numbers and irrational numbers. But today our topic is going to focus on these two numbers. That is what? Rational numbers and irrational numbers. Good. So our topic for today or our lesson is going to focus on these two set of numbers. Good. Now, initially I told you that we are going to look at real numbers. So when we talk of real numbers constitute both rational number and irrational number. So these two set of numbers are what? Real numbers. So we can say that all the rational and irrational numbers are also what? Real numbers. So real numbers. Okay. So when we ask you to give or mention the main types of real numbers, then we are talking about rational and irrational numbers. Okay, good. So we are going to deal with these two numbers. So let's take them one after the other, and then we look at some examples. Okay, now let's tackle with the rational numbers. So rational numbers, good. Good. So rational numbers, what are they? What are rational numbers? So remember also in the junior high school mathematics, we said that rational numbers, they are numbers that can be expressed as a ratio of two integers. I repeat, rational numbers are numbers that can be expressed as ratio of two integers. So we say that rational numbers, or yes, they can be expressed. They can be expressed as the ratio as the ratio as the ratio as the ratio of two integers two integers. So this is what? Rational numbers. Okay, so in other words, we can also say that rational numbers can be expressed as what? Common fraction. They can be expressed as, or can be expressed as so we said that it can also be expressed as common fraction in a form A on B, where A and B are integers, but B shouldn't be equal to 0. So this is what? Rational numbers. Now we said that rational numbers, we can use letter Q. to represent what or denote set of rational numbers. Why are we using Q? We are using Q because we are saying that real numbers can also be expressed as quotient of two integers. Quotient of two integers. So the word quotient, that is why we are using what Q to denote rational numbers. So if you see Q in the real number system, what we all right. So rational numbers, we said we are using hot Q because of its quotient of two integers. All right, great. Now let's look at some examples. So because we are saying that it can be expressed as common fractions, let's think about some types of fractions. So what are some of the types of fractions? We can talk of proper fraction, improper fraction, mixed fraction, liked fraction, and liked fractions. All these fractions are examples of what? Rational numbers. So, if we talk of these examples, then let's write some of these fractions, these common fractions, as examples of um, rational numbers. So examples, so we can write proper fraction. So if I have 1 on 2, this is a proper fraction. It's an example of what? Rational number. If I write this 3 on 2, this is improper fraction because the numerator is greater than the denominator. So this is also what? Improper fraction. And it is an example of a rational number. Let me write mixed fraction, 1 whole number, 2 on 3. So this example is also a rational numbers. Now, when we talk of rational numbers, we can talk of both negative and positive what? Integers. Both negative and positive fractions. They are all examples of what? Rational numbers. So rational numbers do not deal with only positive numbers, but negative what? Numbers. So if we are talking about negative numbers, which are also what? Fractions. So I can write here as negative what do you call it? Negative 2 on 5. So this is also what? A rational number. Now, these are examples. We can also talk about percentages. Percentages. So if I give you 80%, then this is also what? Rational numbers. Okay, good. This is also rational numbers. Now, let's take note of something. The whole number, natural number, set of integers, all these examples constitute what? Rational numbers. So we can have negative and positive integers. They are all examples of what? Rational numbers. So if I write 2, it's an example of what? Rational numbers. So most of the time, students, when you say rational numbers, if you give them whole numbers, they always argue that, but say, we said that rational numbers can be expressed as common fraction or quotient of two integers. So why are you giving me whole numbers? Because whole number is not written in a fraction form. But they have forgotten that all whole numbers can also be written in a fraction form. If I give you 2, if I write 4 divided by 2, this is what? Improper fraction. And what answer am I going to get? If I should divide 4 by 2, am I not going to get 2? So because these 2 wasn't expressed as common fraction, are you saying that it's not an example of rational number? Yes, it is. Okay, because 2 can also be expressed in this form. We can also express other fractions which will also give 2. So all that I want you to understand is examples of whole numbers, examples of natural numbers, integers, They are all examples of what? Rational numbers. Okay, great. Now let's also look at decimal fractions. Decimal fractions. So I want us to look at these ones. When we talk of rational numbers, we can have decimals which are what? Terminating. So we can talk of terminating decimals. Terminating decimals. What do you mean by terminating decimals? So when we say terminating decimals, we are talking about decimal numbers which what has an end value after the decimal point. Okay, so that means a decimal numbers what ends. Okay, so if I give you examples, so let's look at some examples of terminating decimals. So let me see some examples of terminating decimals. If I write this 2.25, this is what? A terminating decimal, because after the decimal point I have 25. Okay, 25. The last number, it ends at what? 5. Okay, so it means that there is no number after what? 5. So this is what a terminating decimals. A decimal that ends. Okay, that when the decimal, after the decimal point, the numbers can what end. We can see the last what number. That's what terminating decimal. So all these terminating decimals are also what? Examples of rational numbers. So when he asks you to give examples, you should be able to tell or give some of these examples. So let me add more of terminating decimals. I can have here as 3.45, 0.334. Okay, so all these examples of what? Terminating decimals. Okay, so rational numbers can also be terminating decimals. Let's also look at another decimal. We can also talk about what? Recurring decimals. Recurring decimals. Good. When we talk of recurring decimals, what do we mean by recurring decimals? So we're talking about decimal numbers that has what? Or decimal numbers that have repeating patterns. They have repeating patterns. You see that after the decimal point, the last decimal number keeps on repeating. It keeps on repeating. It repeats and doesn't end. That's what we refer to as what? Recurring decimals. When the last digit of the decimal number keeps on what? Repeating. Okay, that is also what example of recurring decimal. So let's look at some of these examples. So we can write this 0.3. If I write this as this and I bring this dot, have you gotten that? After that 3 dots, this shows that the 3, which is the last, keeps on what? Repeating. It means if I want to continue, I can continue and go and go and go. It will never end. Okay, right? Good. So you know that this can also be written as 0.3, and then we have this dot on the top. So when I have this dot on the top, this can be written as this. It's the same as this. It means that when I have dot on this 3, it means the 3 keeps on what? Repeating. It doesn't end. So in some books, you may see this or this. They are the same. Okay, so whenever you are expressing this kind of decimals, know how to what? Write them. Okay, all right. Let me add another example. If I write this 0.25 and I bring dot on the 2, what does it mean? I've already told you. It means that the 5 are repeating. Here we saw that it was only 3 that was what? Repeating. But in the case of this example, we once the dot is on both 2 and the 5, it means that both the 2 keeps on repeating. Okay, so once I write this, I can also write it as 0.2525 2, 5. Then let me bring 3 dots, indicating that if I want to continue, I can repeat the 2, 5 and the 2, 5 severally, and it will never end. Have you gotten that? Good. So all these are what examples of rational numbers. So when we talk of rational numbers, we are saying that they are numbers that can be expressed as what common fractions. Common fractions, we can divide them and get what decimal numbers. So all the terminating decimals and the recurring decimals are also examples of what rational numbers. Okay, all right. Now, once we are able to get the idea about rational numbers, then let's proceed to irrational numbers. Irrational numbers. So I'll have my irrational numbers. Irrational numbers. Irrational numbers. Great. So rational numbers, what do you mean by irrational numbers? So irrational numbers is opposite to rational numbers. Okay, so while we can express rational numbers as common fractions, we cannot express irrational numbers as what common fractions. So we say that irrational numbers cannot be expressed as common fractions. As common fractions. Okay, great. So we can't express irrational numbers as a on b, where we say a and b are integers, but b shouldn't be what? 0. We can't express irrational numbers as this in this form. Okay, so that is what we are talking about. Now, if that is the case, then let's see, and which letter can or symbol can we use to denote irrational numbers? Now we can use either q prime, because we are saying that irrational numbers are opposite to rational numbers, and we said that rational numbers or rational numbers are denoted by what the letter what q. So if irrational is the opposite, then we can represent that as what q prime. In some books, you may see I, others even use h, provided they are defined as what irrational numbers. Okay, but in my case, I'm using what q prime because of the definition. We are saying it is opposite to rational numbers, and we use q. Okay, so if it is opposite, then I'm using the prime, the negation part. Okay, all right, great. Let's continue. If that is the case, then let's look at some examples of irrational numbers. Numbers that cannot be expressed as what? Common fractions. Now let's see. So examples we can think of what? This constant pi, what we call pi. Okay, so if you see pi can be what? Written as 3.14159, and then I'll bring my dot. Okay, it means that pi, if I want to continue, I can continue, and it will go and it will go and it will go. It will never what? End. Okay, so pi is one example of what? Irrational numbers. Now let's look at this symbol as well. Now you will be seeing, or you may be seeing, this letter, this small e here. So if you see this e, what name is given to this e? This is what we call what? The Euler's number. Euler's number. This number was developed by a Swiss mathematician and in physics called Leonard um, Ola. Leonard Ola. Yes, that is the name. So because the name is what? Ola, that's why we named this what? Letter or this symbol as a constant. It's a mathematical what? Constant, and it's a number which is so we can say this is what? 2.71828, and that one can also continue. It doesn't what? And these numbers here cannot be expressed as what? Common fractions. Okay, all right, great. Let's add more examples. Now let's look at some square root of numbers. So if I give you this square root of 2, great. So square root of 2 is also what? Example. Now let's take note, all the square root of prime numbers are irrational numbers. So let me add more. Can have square root of 3. So we know that prime numbers start from 2, we move to 3, we move to 5, 7, 11, 13, 17, 19, and then we move on. Okay, so if you are saying the square root of these numbers are irrational, then let me add more. So all these are examples of irrational numbers. So we can list more. Okay, good. So these are all examples of irrational numbers. Now, let's also look at another example. So when we say we can also find the product of two different irrational numbers. So if I should multiply two irrational numbers, let me pick two irrational numbers here. Let's say I have root 2 times root 3. This gives me what? Root square root of what? 6. And this is also what? Irrational. So when you multiply two irrational numbers, the answer you get will also be what? Irrational. That is what we are saying. So you can just pick two irrational numbers and multiply, and at the end of the day, the result still gives you what? Irrational numbers. Right? Great. We can also talk about rational multiples of an irrational number. So if I pick one rational number and multiply by another irrational number, then the answer I will get will be what? Irrational numbers. Yes. So I can talk of what? Let's say I have these two. These two is what? Rational numbers. If I should multiply by an irrational number, so let me pick 5 here. So these two is what? Rational number. But this 5 is irrational number. If I should multiply these two, the answer I will get 2 root what? 5. This answer you see here is also what? Irrational numbers. Now note this. We can also have negative irrational numbers. So not always that all the examples should be positive, because the examples we have been given are positive. So some students may think that since the examples they are seeing here are all positive, so only positive numbers are irrational. No, the same applies in what? Rational numbers. So let me add some negative numbers. So if I write negative root 2 and negative root 3, these are also examples. Okay, great. Now let's take note of this. Irrational numbers are also what? Non-terminating decimals. So we can have non-terminating decimals that are also what? Irrational numbers. So one, irrational numbers can be non-terminating decimals. They can also be non-recurring decimals. So it means that for irrational numbers, their decimal numbers do not end. The last digit do not end. It does not what? Terminate. Okay, the last number does not terminate. Also, we can also say that it doesn't also have what? Recurring decimals. It means they are decimal numbers, or the last decimal number does not what? Repeat. It doesn't have what? Repeating pattern. Okay, great. So let's look at the par, for instance. You see that we have 3.14159 and the three dots. So the three dots suggest that the 9 here is not the last number. If we want to continue, we can continue and continue, and it will never and ever what? End. You get that? Right. Looking at this one too, 8 is the last number. Doesn't mean 8 ends here. If you want to continue, can continue. There are other numbers. So that means that it is not what the decimal number is not terminating. It doesn't terminate. And in the case of the recurring, we are saying that irrational numbers do not also what? Recur. So looking at this, you could see that none of these numbers are repeating. None of these numbers have what? Repeating pattern. So you're looking at 9. 9 is the last decimal here. You see here, though we have other numbers, but looking at the 9 here, the 9 doesn't have what? Repeating pattern. It doesn't repeat. If you look at 8, 8 also doesn't have what? Repeating pattern. So that is what we are talking about. All these are what? Examples of rational numbers. So I would like us to end today's lesson. So today we have been able to look at these two raw numbers. We have talked about whole numbers, natural numbers, set of integers. We have also talked about set of rational numbers. We have given examples. We have also talked about what? Irrational numbers. We have given what? Examples as well. So I know if you are asked to differentiate between rational and irrational, you'll be able to tell me. Okay? And when you are asked to give examples to, you should be able to give me a lot of examples. Okay? All right. So we shall end here and continue next time. Our next topic is going to be changing or writing decimal numbers to common fraction. Okay, we shall look at where we can change the common decimals or decimal fractions to common fractions, and we also look at how we can write recurring decimals to common fraction. So let's meet some other time. We shall continue. All right. Thank you for watching. Bye bye.